options. Laser point. Now we have a laser point. I'd like to have a paper maybe. The mouse will go better. The paper. Then what I'm proposing to you is to concentrate again on the fundamentals of physics, because we have a problem. This is not a small problem, this is a big problem, and when we shall attempt to solve this problem, we will reach to most interesting results. Go further.
No, with the arrow. The arrow.
From arrows.
Arrow.
Yes. Arrows. Then we perceive the physical world in the in space coordinates in time, and then we can define a velocity field, and we can characterize the objects by mass, and we can define a momentum and finally an energy. And from this energy we find some equations called Hamilton equations. While the Hamiltonian functions has this expression. Now, this description doesn't say anything about the structure of the physical world. About the structure of the physical world, we can find in quantum mechanics. Quantum mechanics means that the particles are described by wave functions in the coordinate space and in the momentum space. And then we define operators for the momentum, for the Hamiltonian, and finally we find a Schrödinger equation. And if we use the Hamiltonian expression in this wave functions, we find this expression, and now we calculate the group velocity to see how these particles move, and find something. The first equation, the first Hamiltonian equation, but the second Hamilton equations is something unbelievable, because a sign minus is missing. With these equations we miss these signs, and that means that something must be wrong here. To get back this sign, we have to put, instead of the Hamiltonian, to put here the Lagrangian. And only now we have correct Hamilton equations for our particle. But now we still have a problem. This is the expression of the Lagrangian. Kinetic energy minus the potential energy. These equations are still not physical, because we have an infinite spectrum, and the physical world is finite, and we should have a finite spectrum. Every time we consider the infinity in physics, we get into trouble. But then I write again these equations, these wave functions with the Lagrangian. We have a possibility to put the relativistic Lagrangian. this gives us a velocity limit. Now the spectrum is finite. And if the spectrum is finite, now everything seems to be correct, and we discover that any phase variation, any time-dependent phase variation, has this simple expression with depending on the space-time interval. And then we notice that we can define a relativistic quantum principle, which means that the scalar time-dependent phase variation of a quantum particle wave is an invariant to an arbitrary change of coordinates, which means interval invariance, it has relativistic kinematics of the particle waves. Then from here we obtain the relativistic kinematics. These are well-known calculations deriving the coordinate transforms between two coordinate systems. And with this Lagrangian, we can define momentum. Then it has this expression, mass, and so the relativistic kinematics is the relativistic. Okay, but now we have a quantum particle. Let's suppose we have two quantum particles. In this case, we have a wave functions of this form and an inversion operators which can have two states, two values, -1 value for fermions. These particles are called fermions, and 1, these particles are called bosons. And now notice that an interchange between these particles means a double rotation with an angle pi. So the inversion operator is the product of these two rotation operators. And we derive the rotation operators and find that it depends on the total angular momentum, but we do not propose any field, any orbital motion, only a motion, a proper motion of the particles. And if we have a proper motion of particles, that means that the two rotational operators with angle pi is of this form, and we obtain the inversion operators of this form, and we find that for the two eigenvalues of the inversion operators, we find two possible spins. A spin 1/2, 1/2, and a spin 1. This is for fermions, and this is for bosons. This is a demonstration that is not found in the usual book. Just Feynman is commenting this relation as a difficult to understand one. Now, let's consider this particle in electromagnetic field. If the particle is in electromagnetic field, that means that the wave functions must be modified somehow by this field. And I consider that this modification, that this phase is modified by a field. And I think to components of the field conjugated to the coordinates and to time, and that means that Lagrangian takes this form. And now we can define the momentum on a well-known relation and obtain the canonical momentum as a sum between the mechanical momentum and the electromagnetic momentum. We need the canonical momentum which satisfies the laws of symmetry, because the operators in quantum mechanics are derived from this symmetry. Then
conjugated to time or to momentum?
This is conjugated. This is conjugated
scalar
to
potential. Scalar potential conjugated to time. Is this right?
Yes, scalar momentum is conjugated to time, and the vector potential is conjugated to coordinates. And we define canonical momentum. And now we think again to our quantum relativistic principle, namely that the time-dependent phase variation of a quantum particle is the same in any system of coordinates. Apply again this principle. And if we apply this principle, we calculate, we can obtain the group velocity in the momentum space and find the well-known Lagrange equation. And we can define the Lagrangian, and we can define, we find from this, with this Lagrangian, we find the Hamilton equation again. But this time, these Hamilton equations are referred not to a classical particles, but to the coordinates, a momenta, in a wave, in a quantum wave. Now, we calculate to obtain the derivative of the Hamiltonian and find that although the vector momentum is a time-dependent function, in fact, we obtain a value not depending on time. That means an energy, a time-conservative function. And for this expression, we can derive this factor. We obtain this factor in this form, and finally obtain the Lagrangian as a function of the canonical momentum. Well-known wave function for the energy. But again, this energy does not refer to classical particles. I refer to coordinates and momenta that can be defined for the waves over quantum particles. By some calculation, we obtain this force that is the derivative, time derivative of the mechanical momentum. We reobtain the Lorentz force. The Lorentz force, depending on an electric field, depending on a field of this form, which we call electric field, and a field of this form, which we call magnetic field. And then we obtain from the equations, or you obtain the Faraday-Maxwell law for the electromagnetic induction, the Gauss-Maxwell law for the magnetic induction flow, and with the gauge condition, we can obtain a Gauss-Maxwell law for the electric field flow, which we note with this as depending on charge. We call this We call this charge density, and this is an electric permittivity depending on on measuring units. Then we have an for the derivative of the electric field, we obtain an expression which can be considered of this for the derivatives of the electric field proportional to as a sum of the current density and the derivative of the electric field. Then we still not have all the Maxwell equations. We have only three. To obtain the fourth equation, we must consider for the electric and the magnetic field a relation similar to the Faraday-Maxwell law of the electromagnetic induction. It is, but these are changed. In the Faraday-Maxwell law of the electromagnetic induction, we have a magnetic field variation generating an electric field. Here we have the reverse. An electric field variation is generating a magnetic field. That means that from these expressions of the wave functions of the quantum particles, we obtain the Maxwell equations. But we obtain more. As everybody knows, we obtain wave equation with the propagation velocity c. So we have a spectrum. We have a spectrum with velocity, with the maximum velocity c, and an electromagnetic field with another velocity which is the same, must be the same. From physical point of view, these two velocities of the maximum wave propagations of the particle and the field velocity must be the same, because otherwise it's no physical sense. We could have field waves not interacting with anything, which is not possible because we don't know about such a field, or we can have a particle propagating with the velocity without any possibility to interact with this particle, with the field. So the two velocities must be the same. This is a wave package describing a particle and with the maximum velocity, which is the same with the light velocity. Now, I have written again the Lagrangian, which is in fact the time-dependent phase of the quantum particle. And we, as a group velocity, we obtain the Lagrange equation. If we have the Lagrange equations, that means that in fact we obtain the least action principle. And from the least action principle, we obtain by some simple calculations, we obtain the Lorentz, again the Lorentz force and the expressions for this four-field tensor. Four-field tensor derived, which is an expression of the vector field we initially derived in the interaction with the electromagnetic field. Further, if we consider transformations between two from the invariance of the time-dependent phase, we obtain a mechanical component of this phase and an electromagnetic component, and this must be zero. This variation must be conserved. The electromagnetic component also must be conserved, and we finally obtain, as a function of the transform matrix, we obtain the field transformation. Then we have this matrix of transformation of coordinates. From this, we obtain finally the transformation of the fields. Now, we come again to the Schrödinger equation, because for a life we solved the Schrödinger equation, not something else. And we found that in fact the wave function of a particle is the Schrödinger equation, this, with a rapidly varying factor. And we solve, in fact, equations for the amplitudes of the particle field, for the particle wave functions. And now comes a well-known calculation of Dirac, but this again refers to momenta and coordinates of the wave functions. And we can write this Hamiltonian in this form. It is a function with the well-known operators of Dirac, which depend on the Pauli spin operators, and so on. We obtain Schrödinger equation takes this form with two components, and we obtain this Schrödinger equation. What is interesting that if we eliminate the couplings between two equations, this is the equation for C1 with the coupling term for C2, the coupling term for C1. It is interesting that in a non-relativistic approximation, we obtain, here we obtain the classical energy, and here something that is approximatively the 2 times the relativistic rest energy. And finally, the two equations are in fact a single equation of this form, but for the two components. Then we consider a quantum particle in magnetic field. We consider the operators of the mechanical momentum. We finally find that these terms takes these forms depending on the magnetic field. While this is a term describing a rotation. When we have an energy of a particle in a magnetic field, that means that the charged particle rotates somehow. This is the proper rotation in the magnetic field. Then the two equations take this form with the kinetic energy, electric energy, and with a potential energy in magnetic field with this mu s terms, which is for the spin. And by some calculation, we find geomagnetic ratio between the magnetic spin and kinetic angular momentum. The idea is that the Hamiltonian must commute with the total angular momentum, which has two components. Proper components, a proper rotation, and an orbital rotation around some other particles, and a heavier particle. And we generally know the orbital momentum, and finally we calculate the spin momentum, the spin angular momentum, and find the geomagnetic ratio, the ratio between the two momenta. Now, if we then from this quantum relativistic principle, we obtained the kinematics, the relativistic kinematics, the relativistic dynamics, obtained the electromagnetic field and the equations of the electromagnetic field. We obtained the spin, which is an approximation for the non-relativistic case. The full relativistic equations I have not solved yet. Maybe I will solve never. Now, I write these expressions of the wave functions generalized in a generalized form for the curvilinear coordinates. And we find this relation. We have here an integral, but we again consider an approximation. Namely, we consider that the particle is small compared to the variations of the coordinates. Sorry, if you have some problem, I'm ready to stop. And then we have to linearize, to obtain again wave function, because this is not this is too complicated to solve something. I wish to obtain wave functions with terms depending proportional to coordinates and proportional to time. And in this linearization, I consider that in the space-time interval, the time is dominant and the space variation are negligible. And due to this, I consider such an approximation of the square root. And I obtain this expression. Here we have some notations. The Roman letters correspond to the to space, to the space coordinates, and alpha, beta corresponds to the 4 coordinates, time included. Then we have the wave packets in curvilinear coordinates take this form, which then proportional to the coordinates and then proportional to time. And when we calculate the group velocity, we obtain something which is coherent. The velocity as a derivative with time is of this form, takes this form, because time is approximately the same with the space-time interval. Then we consider a particle acceleration on a geodesic. And the geodesic equation is this. the acceleration is proportional with this product and with second kind Christoffel symbol. And in this case, we can calculate this acceleration and obtain this equation. We transform this into first kind Christoffel symbol, and after that consider the expression of this symbol on the metric tensor, and we obtain this expression of the acceleration. Here we take into account that we consider a stationary process. If we have a stationary process, these are common mean derivation. Is a notation of Dirac. I took from him, the great architect of the quantum mechanics, make the formalists for the theory of relativity also. And these two derivatives on time are zero. And here we have the derivative of the time coordinate on the space-time interval, which is approximately the same, and obtain the acceleration as a gradient. As a gradient of this element of the metric tensor. If this is a gradient, the acceleration is a gradient, that means that this must be a force. And then we consider the time, the element 0, 0 of the metric tensor in this form. In this form, 1 minus 2. Because otherwise this element is 1. If we have a variation of with space coordinates, must be, this means that we must have a coordinate dependent function. And finally we put this potential. This is a potential, in fact, we put of this form, which is the Newtonian form. And finally, if we continue with this expression, we have the derivative, the gradient of these functions, of this, and finally we obtain a gradient of the form which is somehow similar with the Newtonian expression. And now there is a solution for the matrix tensor for a stationary field, which is called Schwarzschild solution for the matrix elements. And this solution gives us this expression. That means a Newtonian force, but with the correction, with the relativistic correction. So we obtain the three components as a component with R, radial components, and the other components are null. So from our expressions for our wave functions of a quantum particle, we obtained an acceleration in gravitational field, in a gravitational field of one form in the quantum relativity. Then my conclusions. I have here something important that I was going to. We consider the particles has a wave function form. What this means? This means that we have distribution of matter which has waveform. For this matter distribution, we can define a velocity, and we can define space-time interval, which is of this form. And if we make the covariant derivative, what it means covariant derivative, I remember you that is the derivative in the Cartesian coordinates, but written in curvilinear coordinates, where we eliminate the term due to these collinear coordinates, and obtain that the covariant derivative is perpendicular to the velocity. And now, if we consider geodesic equation, geodesic propagation of this wave, or wave, and we take another, an additional acceleration. If we take an additional acceleration, by some calculation, we find that this acceleration can be only perpendicular to the velocity. So if we have a wave propagating in a direction of a geodesic, we can have displacements on a perpendicular directions. It is in the plane of the waves. Then here I find an invariant for the particle density. I consider particle density in the Cartesian coordinates and in curvilinear coordinates, and the expression of the density in curvilinear coordinates, and consider this a normalization of the wave functions. That means an integral of the density of the mass density into coordinates in system S prime and a system S, and these are connected with the Jacobian. What is interesting that this Jacobian is this form. If we consider the tensorial transformation of the metric tensor, we obtain here elements of the Jacobian determinator. And that means that the determinant of this matrix is the product of all these determinants, which means that the determinant of the metric tensor is the square of the Jacobian multiplied with the density, with the metric determinator in the other space of coordinates. So I obtain these expressions connecting the determinants G of the metric tensors in the two coordinates. So if I put this ratio here, the ratio of the Jacobian here, we obtain an invariant for the density, or the meta density. And this is invariant is the density with the square of minus G, the determinant of the metric tensor, which is negative. so due to this I have put 1. Because we have for the diagonal 1 for time and -1, -1, -1 for the 3 space coordinates. And I want to define here a relation for the matter conservation, and for this I consider flow vector, flux density is the product of the density with the velocity. And if we, the matter conservation means a small covariant divergence. Again, I make the covariant derivations, the covariant divergence, and this must be 0. We see that, at last we see that this means a meta conservation. And I calculate again this second kind Christoffel symbol with well-known relations, and find this expression of this symbol, the derivative of this, the square of this determinant of the square, and multiplying with -g, we finally obtain that the meta conservation defined in this way means, in fact, divergence, a null divergence of this product of the meta flow with a factor -g squared. This is the divergence. And if we have divergence and we make an integration in the 3-dimensional space, we obtain 4 components, and we separate the time components from the coordinate components and obtain this expression which describes meta conservations. The derivative of this expression of this there is the flow through surface for the boundary surface of this volume, which is this. And in the non-relativistic case, this J0 is in fact the density multiplied with the derivative of time against the space integrand, which is 1. J0 is rho, and Jm is rho, this velocity, the spatial velocity. So in this way we define a quantum particle here is understood as a meta distribution which is conservative. This method is conservative. Then my conclusion are the following: that we formulated a relativistic quantum principle, asserting that a quantum particle is described by a wave packet with a finite spectrum and invariant time-dependent phases to an arbitrary change of coordinates. Based on this principle, we derived a unitary relativistic quantum theory, the relativistic kinematics of a quantum particle, the relativistic dynamics of a quantum particle, the Maxwell equations of a field interacting with a quantum particle, the dynamics of a quantum particle in an electromagnetic field, the relativistic electrodynamics, the spin of a quantum particle, the relativistic dynamics of a particle in gravitational field as a deformation of the space-time matrix. Then you see that the electromagnetic field is a modification of the time-dependent phase, while the gravitational field is a deformation of the coordinates. These two forces are completely of different nature. Thank you.
Any questions?
I'll start with questions.
Please.
Can I go back to your second slide, please, where you're upset with the Hamiltonian?
The second slide.
Oh, maybe it's the third slide, sorry. Maybe the third slide. Where you're, that's it, where you're unhappy with the Hamiltonian. At the bottom. Basically, what you have there is the kinetic energy of the mass plus the potential field. Why does nobody ever include the kinetic energy of the spin energy of the particle in that?
Why you have? Because I obtained this spin later. I obtained.
It's already there.
Yes, I could introduce, but I hadn't yet this. I have this only describing a particle as a wave packet.
Okay, but what you actually have there is, in a particle, you always have its mass energy and you have its spin energy. The two are the same size. So the kinetic energy of the mass is already there with a half mv squared effectively. You should have the kinetic energy of the spin as well. In which
Yes,
case,
but
when they're equal, you have zero energy, so you have stable.
yes, but this is still an approximate equation that is not the equation of the theory. Is the equation of an old theory. I could introduce this. Okay, I could introduce, but after that, I show that the time dependence, the time dependent phase must be of this form with the Lagrangian instead of the Hamiltonian. And only in this case I obtain Hamilton equations.
Okay, but you're doing that because you're using it as a wave. With the particle, everyone is forgetting the kinetic energy of that spin.
Yes, I haven't introduced because it was not in my purpose. It was not my purpose to refer to this spin. The only important thing here is that this wave equation and the Schrödinger equation leads to wrong Hamilton equations for the particle. This was my purpose. I could introduce it, but I had no reason to refer to this. Most important is that I do not obtain the Hamilton equations.
Any other questions? No questions? Yes?
Is it possible to get a tachyon?
Or tachyon? I don't know.
It doesn't
This is
depend
all
on
I
the
need.
No.
I don't know.
Can it appear?
Because it's not a finished theory. I spoke only the electromagnetic interaction.
No, you consider a charged particle in gravitational field.
Yes.
Can you have solutions with exceeding the speed of light?
Wait.
Exceeding the speed of light.
Exceeding
the speed of light.
No.
Never.
This is in agreement with the theory of relativity, in agreement with the electromagnetism, with the quantum mechanics. The only thing that I obtain all this from the description of a quantum particle. I don't know. For instance, I do not derive the nuclear interactions. I don't know what will happen. consider. In any case, this is a weak interaction because this field is constant for all the waves of the particles.
I mean that in very standard theory, which is of course relativistic and quantum, but superluminal propagation appears. In some, it depends upon approximation upon the external metric.
I don't believe in superluminal, but this is another point.
Nobody
I think
believes,
I
but
don't-
solutions appear.
Which solutions? Next time you'll show us solutions of what? It's
For field equations.
Field equation. Which equations? Field equation, but not of Maxwell equations.
Maxwell, of course.
Maxwell?
Maxwell, of course, with radiative correction.
With
With
other
radiative correction.
with connections.
Corrections.
With correction.
correction.
I don't see how we should correct because I showed here that the Maxwell equations are correct and in agreement with the properties of interaction with the quantum particle. I don't know which corrections we need. For what? Corrections for what?
For self-interaction of photons, for instance.
For?
Self-interaction of photons. All quantum relativistic corrections.
Corrections.
For interaction of photons.
Interactions of photons
With themselves, for instance.
with themselves.
Yeah.
Interactions between photons.
Yes.
Light by light scattering.
And which is the cause of interactions?
Light by light scattering. The simplest example.
How they interact?
According to this diagram with four lights.
Which is the process?
The process-
Which is you have two electromagnetic fields.
No,
how
they-
this,
for-
this electromagnetic
It's mediated by virtual variations.
can add one another.
Yes.
Can-
You asked what process. The basic process is the creation
I
of
think
electron
that-
positron pair by photon.
I think that the an interaction between two electromagnetic fields is a nonsense because we cannot distinguish one another two electromagnetic fields. We cannot distinguish. How you distinguish this field when they superpose one another? How you know which is a field and which is the other? Because we have here in this region only electromagnetic field. Which field? Probably there are many theories.
I mean that there are well-established. This is a well-established thing that there are radiative corrections to every process, including, and they create interaction between photons and many other things. And with
How
this,
you distinguish the two photons when they superpose one another? How if they interact, they must be of different nature. How you can say this is the photon 1 and this is the photon 1, 2, and they interact and produce, I don't know.
well, the same way if there are two electrons that interact between themselves.
If I know that there are two electrons. And you don't know, and then you have, if you have two electrons, you have two electron states. That is
I suggest you can discuss it later because we have the time for the next talk.
how you wish.
Yeah.
You are
Thank you
I think
very
it's
Sorry,
good.
sorry.
Professor Stefanescu.